Hello friends, in today's podcast we are going to discuss about p block elements. We already published an episode on p block elements for class 11th chemistry students, and this podcast is on p block elements for class 12th chemistry students. So first, p block elements definition. The p block elements are defined as the elements in the periodic table in which the last electron enters in the p orbital of the atom. P block elements classification. P block elements are classified into 6 groups as follows: group 13, group 14, group 15, group 16, group 17, group 18. In group 13, last electron goes in p orbital having electronic configuration ns2 np1. For group 14, electronic configuration is ns2 np2. For group 15, ns2 np3. For group 16, ns2 np4. For group 17, ns2 np5. For group 18, ns2 np6. And and now group 15 elements of p block elements. The group 15 elements includes nitrogen, phosphorus, arsenic, antimony, bismuth. Symbol of nitrogen is N, symbol of phosphorus is P, symbol of arsenic is As, symbol of antimony is Sb, symbol of bismuth is Bi. As we move down the group in periodic table, the metallic character increases with increase in atomic number. Nitrogen and phosphorus are non-metals. Argon and antimony are metalloids, while bismuth is a metal. Occurrence: nitrogen gas N2 is occupied by the 78% of the total atmosphere. It is the main component of the proteins which play many critical roles in our body. It occurs as sodium nitrate in the Earth's crust. Phosphorus occurs as minerals of the apatite family, that is Ca9PO46.CaX2, where X is fluorine, chlorine, or OH. It is present in the form of proteins in milk and eggs. It is also present in bones and living cells. Arsenic, antimony, and bismuth are generally associated with sulfide minerals. The main ore of bismuth are Bi2O3 and sulfide Bi2S3. Electronic configuration. The general electronic configuration of group 15 elements is ns2np3. The outermost 3 electrons are unpaired in p subshell. Since D and F subshell are absent in N, P and present in As, Sb and Bi, that makes nitrogen and phosphorus behave differently from arsenic, antimony and bismuth. Elements: nitrogen having symbol N, atomic number 7, condensed electronic configuration is He2s2 2p3. Phosphorus symbol P, atomic number 15, condensed electronic configuration is Ne3s2 3p3. Arsenic symbol As, atomic number 33, condensed electronic configuration Ar3d10 4s2 4p3. Antimony symbol Sb, atomic number 51, condensed electronic configuration Kr 4d10 5s2, 5p3. Bismuth, symbol Bi, atomic number 83, condensed electronic configuration Xe, 4f14, 5d10, 6s2, 6p3. Physical properties. As we move down the group from nitrogen to bismuth, covalent, ionic radii and metallic character increases and value of ionization enthalpy and electronegativity decreases. Nitrogen is the most electronegative elements in the group 15. Nitrogen is a gas and exists as diatomic molecule with a triple bond between the atoms. Phosphorus, arsenic and antimony probably exist as tetraatomic molecule containing single bonds between each pair of atom. Bismuth is monoatomic metal. The density, atomic volume and boiling points increases down the group of group 15 elements. Allotropy of group 15 elements. Allotropy is the existence of two or more different physical forms of a chemical element. Nitrogen in its solid state exists in two forms, cubic crystal structure and hexagonal crystalline structure. Phosphorus exists in three forms, namely white, red and black phosphorus. White phosphorus is waxy solid of P4 tetrahedral and it is also available in gaseous state. Red phosphorus has complex chain structure while black phosphorus is thermodynamically stable having layer structure. Arsenic and antimony also exist in three allotrophic forms. Bismuth does not show any type of allotropy. Chemical properties. Action of air. With oxygen, all the elements of group 15 to corresponding oxides on heating. That is N2 plus O2 gives 2NO. Action of acids. There is no action of hot concentrated nitric acid HNO3 on nitrogen, but with phosphorus and arsenic they form oxyacids, while antimony and bismuth forms oxides and nitrates respectively. P4 plus 20 HNO3 gives 4H3PO4 plus 20 NO2 plus 4H2O. Action of alkalis NaOH. Nitrogen have no action of alkalis, but phosphorus form phosphine and hypophosphite. Action of metal. Nitrogen forms metal nitrides. 6Li plus N2 gives 2Li3N. Phosphorus form metal phosphides. 6Mg plus PO4 gives 2Mg3P2. Arsenic and antimony forms covalent arsenides and antimonides respectively. Reactivity towards hydrogen. In group 15, all elements form hydrides with formula AH3, where A is equal to NPASSBBI. Example NH3, PH3, etc. Basicity and thermal stability. These hydrides decreases in the order of NH3 highest, then PH3, then ASH3, then SBH3, then BiH3 lowest. That is down the group. Oxidation states. Since the general electronic configuration of group 15 elements is NS2NP3, they show common oxidation states of +3, +5 and -3. Nitrogen shows wide range of oxidation states from -3 to +3. From N to Bi, +3 oxidation states increases and +5 oxidation states decreases. Nitrogen in its solid states exists in two forms. Nitrogen. Abnormal behavior of nitrogen. Nitrogen differ in other elements of group 15 due to small size, high electronegativity, high ionization enthalpy, and absence of d orbital. Nitrogen is a gas while all other elements of the group are solid under normal temperature. Nitrogen exists in diatomic molecule N2 while all other elements of group exist in tetraatomic molecules P4, Sb4. Nitrogen can form p-pi multiple bonds while other elements forms d-pi overlapping. Nitrogen does not form pentahalides like other elements in group. Nitrogen shows variable range of oxidation states while other elements of group shows limited oxidation states. Nitrogen is highly electronegative element with absence of d orbital. Preparation of dinitrogen N2. Commercial method. On commercial scale, it is prepared or obtained by the fractional distillation of liquid air. Laboratory method. It is prepared in the laboratory by reaction of ammonium chloride on sodium nitrite from ammonium dichromate. Dinitrogen is obtained by thermal decomposition of ammonium dichromate from sodium and barium azide. Nitrogen is obtained in pure form by thermal decomposition of sodium or barium azide. Properties of dinitrogen N2. Dinitrogen is present in the atmosphere in gaseous state. It is odorless, colorless, tasteless, and chemically inert and non-toxic gas. It is slightly soluble in water and it has low freezing point, that is about 195.3 Kelvin. At room temperature, it is chemically inert. As temperature increases, its reactivity also increases. Dinitrogen combines with dioxygen to give nitric oxide at about 2000 Kelvin temperature. On reaction with carbide, it gives calcium cyanamide. Compounds of nitrogen. Ammonia NH3. Preparation of ammonia. First, laboratory method. Ammonia is obtained by heating a mixture of NH4Cl and slacked lime CaOH2. Manufacturing method. Ammonia is manufactured by Haber's process on large scale. In this process, N2 and H2 are in proportion of the ratio of 1:3 are allowed to react at high pressure, that is 200 into 10 to power 5 Pascal and temperature about 700 Kelvin. The catalysts used in this process are Fe2O3, K2O and Al2O3. Properties of ammonia. Ammonia is colorless gas having pungent smell and can be toxic. Its freezing point is 198.4 Kelvin and boiling point is 239.7 Kelvin. It is highly soluble in water to form NH4OH. It burns in the excess of air to give dinitrogen and water. It reacts with Cl2 to give NaCl3. It gives amide to react with active metals like Na and K, that is sodium and potassium. Uses of ammonia. It is used to prepare ammonia nitrate, urea, ammonia phosphate, ammonia sulfate, fertilizers, nitric acid, and it is also used as refrigerant. Nitric acid HNO3. Laboratory method. By distillation of nitric with concentrated sulfuric acid. Commercial scale. On commercial scale, large scale, nitric acid is prepared by Ostwald's process. It is prepared by 3 steps. First, NH3 is oxidized by atmospheric oxygen in presence of catalyst. Nitric oxide NO combines with nitrogen to gives NO2. Nitrogen dioxide dissolves in water to gives nitric acid. Properties of nitric acid. Pure nitric acid is colorless liquid having freezing point of 231.4 Kelvin and boiling point of 355.6 Kelvin. In gaseous state, it is planar molecule. The pure nitric acid is unstable. Uses of nitric acid. Nitric acid is used in the manufacture of organic dyes, varnishes, cellulose. It is used in the preparation of sulfuric acid in lead chambers process, and it is also used as oxidizer in rockets fuel. Oxides of nitrogen. Nitrogen can form number of oxides in its different oxidation states. Name of oxide: dinitrogen oxide N2O. Oxidation states of nitrogen is +1. Physical appearance and chemical nature: colorless gas and neutral. Name of oxide: nitrogen monoxide NO. Oxidation states of nitrogen +2. Physical appearance and chemical nature: colorless gas, neutral, reactive. Dinitrogen trioxide N2O3 having oxidation states of nitrogen +3. Brown gas, acidic and reactive. Nitrogen dioxide NO2 +4. Blue solid, acidic. Dinitrogen tetraoxide N2O2 +4. Colorless solid or liquid, acidic. Dinitrogen pentaoxide N2O5 +5. Colorless ionic solid, unstable, acidic. Phosphorus. Allotropic forms of phosphorus. Phosphorus is present in 3 allotropic forms, that is white, red and black phosphorus. White phosphorus, it is translucent white waxy solid insoluble in water. It is stored in water to protect from air. It has tetrahedral structure P4. Red phosphorus, it is tasteless, odorless, non-poisonous, reddish violet solid in powder form. It is less reactive than white phosphorus. In red phosphorus, P4 tetrahedral units are linked to each other to form chain. Black phosphorus, it is thermodynamically most stable allotrope. It does not react with water. It has 2 different forms: alpha black phosphorus and beta black phosphorus. Compounds of phosphorus. Phosphine pH3. Preparation. Phosphine is prepared by action of water on calcium or aluminium phosphide. Properties of phosphine. It is colorless gas having odor of rotten fish. It is highly poisonous and soluble in water. It does not react with acid and alkalis but reacts with oxygen to form explosive. Uses of phosphine. It is used in the preparation of smoke screens, organophosphorus compound. It is used as powerful reducing agent. Phosphorus halide. Phosphorus can form 2 types of halides, namely phosphorus trichloride with general formula PX3 and phosphorus pentachloride with formula PX5. Where X is fluorine, chlorine, bromine, iodine. Group 16 elements of p block elements. Group 16 elements include oxygen, sulfur, selenium, tellurium, and polonium. Since first four elements of group forms ore, that is oxides, sulfides, etc. with number of metals, they are called as chalcogens. Occurrence: oxygen is present by mass 46.6% and in atmosphere 21% by volume. Sulfur is less abundant. Cesium and tellurium occurs as sulfide, while radioactive polonium occurs by decay of thorium and uranium. Electronic configuration. The valence shell electronic configuration of group 16 is NS2Np4. Elements: oxygen, atomic number 8, condensed electronic configuration He2S2 2p4. Elements: sulfur, atomic number 16, condensed electronic configuration Ne3S2 3p4. Selenium 34, Ar3d1. Tellurium 52, Kr3d10 5s2 5p4. For selenium, Ar3d10 4s2 4p4. Polonium 84, Xc5d10 6s2 6p4. Trends in physical properties. Except oxygen, all the other elements of group are solid at common temperature or room temperature. Sulfur and selenium exists in crown puckered ring structure of 8 atoms. Due to addition of new shell, the atomic as well as ionic radii increases down the group. Metallic character increases down the group. Sulfur is non-metal, selenium and tellurium are semi-metals, while polonium is metal. Oxygen shows less possibility towards catenation. The tendency of catenation decreases down the group. Density of group increases down the group due to increase in atomic mass. Metallic and boiling point increases down the group except PO. Oxygen is second most electronegative element after fluorine. The value of electronegativity decreases down the group. Chemical properties. The reactivity of elements decreases down the group. The group 16 elements react with oxygen to form dioxides S plus O2 SO2. Sulfur reacts with alkalis to form sulfides and sulfides with nonmetals. Group 16 elements combine directly. All the group 16 elements are weakly acidic and act as weak diprotic acids. All the hydrides of these groups are reducing agent except H2O. These elements of group can form large number of halides with formula AX6, AX4, AX2, where A is the element of group 16. Abnormal behavior of oxygen. Oxygen differs from all the elements in group ion several properties due to its small size, absence of d orbital, high electronegativity. Oxygen is a gas while other elements are solid. Hydrides of oxygen is in liquid state, that is H2O, while other are in gaseous state. Molecular oxygen is paramagnetic while other elements are dimagnetic. Oxygen exists in diatomic molecule O2 while other elements are in polyatomic. Dioxygen O2 preparation. Naturally, by photosynthesis. Dioxygen is produced in atmosphere in large quantity by photosynthesis of green plants. XH2O plus XCO2 in presence of sunlight gives CH2OX plus XO2. Laboratory method. In this method, dioxygen is prepared by heating KClO3 using catalyst MnO3. 2KClO3 gives 2KCl plus 3O2. Commercial method. On large scale, O2 is prepared by two methods. From water. By electrolysis of acidified water, O2 gas is obtained at cathode. From air, O2 is obtained by fractional distillation of liquid air. By thermal decomposition, dioxygen can obtained by thermal decomposition of oxygen-rich salts and metallic oxides. 2KNO3 gives 2KNO2 plus O2. 2H2O2 gives 2H2O plus O2. Properties of dioxygen. Dioxygen is odorless, colorless, tasteless gas which is heavier than air, and it is the basis of life on the earth. It is paramagnetic. It is also present in water in dissolved form, which help to sustain life of plants and animals in water. It has three stable isotopes, that is 16O, 17O, 18O. It does not show much chemical reactivity. It is quite stable at room temperature or normal temperature. Dioxygen is not combustible but supports combustion. It forms oxides with different form of metals. Oxides are classified into three types: acidic oxides, basic oxides, amphoteric oxides. Acidic oxides are the oxides which combines with water to give an acid is called as acidic oxides. Basic oxides, the oxides which combines with water to give an base is called a basic oxides. Amphoteric oxide, the oxides which show acidic and basic character are called as amphoteric oxides. Uses of dioxygen. It is most important gas for all living organisms for respiration. Dioxygen is used firemen, sea divers, miners, aviators, and also useful for artificial respiration in hospitals. It is used in rocket fuel, metallurgical processes, and in the preparation of large number of compounds. Ozone, O3. By the action of electrical discharge or ultraviolet radiation on dioxides, ozone can be obtained. It is present at the height of 20 km from Earth's surface. This layer is called ozonosphere. Ozone O3 prevents entry of harmful high energetic ultraviolet UV rays. It is formed in atmosphere naturally through photochemical reaction. Preparation of ozone. By laboratory method, slow dry steam of dioxide O2 is passed through a silent electric discharge. Dioxide O2 gets converted into ozone O3. 3O2 gives 2O3. Properties of ozone. Ozone is thermodynamically stable, having pungent odor. Solid ozone is violet black, liquid ozone is blue black, and gaseous ozone is blue. In higher concentration, it is very dangerous explosive. Uses of ozone. It is used as disinfectant and germicide, sterilize air and water bleaching agent for starch, oils, waxes, flour, etc. In industry, it is used in the manufacture of silk and camphor. It prevents the harmful ultraviolet UV rays from sun from reaching the earth's surface. Sulfur. In free state, sulfur occurs in the volcanic regions. It is also occurs in combined state as sulfides Fe, S2, ZnS, HgS, Cu2s and sulfates MgSO4 dot 7H2O, CS4 dot 2H2O. Sulfur exists in different allotropic forms as follows: rhombic sulfur, monoclinic sulfur, cyclo-S6, milk of sulfur, plastic sulfur, SN molecular sulfur, colloidal sulfur. Compounds of sulfur. Below are compounds of sulfur, that is sulfur dioxide SO2. Preparation: sulfur dioxide SO2 is obtained when sulfur burns in air. S plus O2 gives SO2. In laboratory method, sulfur dioxide is obtained by the action of sulfuric acid on copper turnings. Cu plus 2H2SO4 gives CuSO4 plus SO2 plus 2H2O. On commercial method, it is on large scale produced by product of a roasting of pyrites. 4FeS2 plus 11O gives 2Fe2O3 plus 8SO2. Properties of sulfur dioxide SO2. Sulfur dioxide SO2 is colorless with pungent and suffocating smell. It is highly soluble in water to form sulfurous acid S2 H2SO3, that is SO2 plus H2O gives H2SO3. Its boiling point is 263 Kelvin. In solid state, it forms discrete molecules. It is reducing agent. Uses of sulfur dioxide SO2. It is used in the manufacture of H2SO4 and refining of petroleum and sugar industry. It is used as disinfectant, preservative, germicide, bleaching agent and solvent. Sulfuric acid H2SO4. Manufacturing process. Contact process. This process involves 4 basic steps. Preparation of sulfur dioxide SO2 from sulfur. S plus O2 gives SO2. Oxidation of sulfur dioxide and sulfur trioxide SO3 by using catalyst vanadium pentaoxide V2O5. 2SO2 plus O2 gives 2SO2. 2SO3. Sorry, reaction is as 2SO2 plus O2 gives 2SO3. By dissolution of sulfur trioxide SO3 in sulfuric acid H2SO4, oleum H2S2O7 is obtained. SO3 plus H2SO4 gives H2S2O7. Dilution of oleum H2S2O7 to give sulfuric acid H2SO4. So H2S2O7 plus H2O gives 2H2SO4. Lead chamber process. In this process, a mixture of SO2, NO, air is treated with steam to obtain H2SO4, that is 2SO2 plus O2 plus 2H2O gives 2H2SO4. Properties of sulfuric acid H2SO4. Sulfuric acid H2SO4 is colorless, dense, oily liquid with boiling point 611 Kelvin and freezing point 283 Kelvin. It is strong acid, less volatile and highly viscous due to hydrogen bonding. It is known as king of chemicals. It acts as dehydrating agent with many organic compounds. HCOOH formic acid in presence of H2SO4 gives CO plus H2O. C6H12O6 glucose in presence of H2SO4 gives 6C plus 6H2O. It also acts as oxidizing agent. S plus H2SO4 gives 3SO2 plus H2O. P4O10 plus 6H2O gives 4H3PO4. When metals are treated with sulfuric acid, H2SO4 gives out hydrogen. Fe plus H2SO4 gives FeSO4 plus H2. Uses of sulfuric acid H2SO4. It is used in the preparation of HNO3, HCl, H3PO4, Na2CO3, sulfide, oleum, ether, etc. It is most important chemical in many industries for manufacturing of dyes, fertilizer, detergents, explosives, etc. It is used in lead storage batteries. It is also used as laboratory reagent, dehydrating agent and oxidizing agent. Group 17 elements. Group 17 elements halogens of phosphorus or of p block elements. Group 17 elements includes elements fluorine, chlorine, bromine, iodine and astatine. These elements are highly electronegative, which are found in seawater as salts. Astatine is radioactive element. Electronic configuration. The outermost cell electronic configuration is ns2np5. Each of them is only short of one electron to get stable noble gas electronic configuration. Element fluorine, atomic number 9, condensed electronic configuration He2s2 2p5. Element chlorine, atomic number 17, condensed electronic configuration Ne2s2 2p5. Elements bromine, atomic number 35, condensed electronic configuration 3d10 4s2 4p5. Element iodine, atomic number 53, condensed electronic configuration Kr 4d10 5s2 5p5. Element astatine, atomic number 85, condensed electronic configuration Xc 4f14 5d10 6s2 6p5. Physical properties. All these elements of group 17 are exist in diatomic form F2Cl2Br2 etc. Fluorine and chlorine are in gaseous state while bromine is liquid and iodine is in solid state at normal temperature. On moving down the group 17, atomic ionic radii increases while ionization enthalpy decreases. All the elements of group possesses very high value of electronegativity. Fluorine is the most one. This value decreases down the group to iodine. All halogens are typically non-metals having low melting and boiling points. To attain stable noble gas configuration, halogens show common oxidation state, that is 1. They also show positive oxidation state, that is +1, +3, +5 and +7, but most common oxidation state is -1. Chemical properties. Halogens are highly reactive elements. the reactivity decreases down the group. Halogen has a strong tendency to accept an electron to form anions. They act as a strong oxidizing agent. On reaction with metals and nonmetals, halogen forms halides. Cu plus F2 gives CuF2. 2Al plus 3Br2 gives Al2Br6. Halogens reacts with hydrogen to give hydrogen halides. H2 plus F2 gives 2HF. H2 plus Cl2 gives 2HCl. All the halogens react with NaOH to form halides and hypohalides. 2NaOH plus 2Cl2 gives 2NaCl plus NaOCl plus H2O. Halogens combines amongst themselves from many compounds known as interhalogen compounds. Abnormal behavior of fluorine. Fluorine abnormal behavior due to high electronegativity, small size, low FF bond dissociation energy, non-availability of d orbital in its valence shell. It is highly reactive element which form hydrogen bonding in its hydrides. It exhibits only in -1 oxidation state. Dear friends, you can download notes of this chapter in PDF form from our website www.chemistrynotesinfo.com. You can follow us on YouTube, Facebook, Instagram and Twitter. Chlorine. The chlorine is greenish yellow poisonous gas, occurs in extent of 0.14% in earth crust, and chlorine is also present in seawater as KCl, MgCl and CaCl2. Preparation of Cl2 by the oxidation of HCl on manganese dioxide MnO2. MnO2 plus 4HCl gives MnCl2 plus Cl2 plus H2O. On commercial scale, it is obtained by Deccan process. HCl is oxidized by atmospheric oxygen. 4HCl plus O2 gives 2Cl2 plus H2O. Electrolytic process. This process involves the electrolysis of an aqueous solution of brine NaCl. Properties of chlorine. It is poisonous greenish yellow gas with suffocating pungent smell and heavier than air. It is soluble in water and the solution is called chlorine water. Chlorine is neither combustible nor supports combustion. It reacts with number of metals to form their chlorides. 2Na plus Cl2 gives 2NaCl. 2K plus Cl2 gives 2KCl. It dissolves in water to form mixture of HCl and HOCl, hypochlorite acid. Cl2 plus H2O gives HCl plus HOCl. Chlorine reacts with hydrogen with very high affinity to form HCl, that is H2 plus Cl2 gives 2HCl. Uses of chlorine. It is used as bleaching agent for sterilization, extraction of metals like gold and platinum. It is used in the manufacture in bleaching powder, dye stuffs, explosives, refrigerant, several poisonous gases, hydrochloric acid, plastics, insecticides and several industry solvents. Hydrochloric acid HCl. It is colorless gas with pungent odor. In liquid state, its boiling point is 189 Kelvin and melting point is 159 Kelvin. It is
highly soluble in water. Hydrogen chloride HCl is prepared laboratory by heating a mixture of sodium chloride and concentrated sulfuric acid. NaCl plus H2SO4 gives NaHSO4 plus HCl. Uses of hydrochloric acid HCl. It is used in manufacture of chlorine, ammonium chloride and glucose. It is also used in medicine, galvanizing, preparation of H2 and as a laboratory reagent. Interhalogen compounds. The compounds obtained from different halogens are called interhalogen compounds. The general compound of interhalogen compounds are XX-, XX-3, XX-5, XX-7, where X is electropositive group halogen elements. XX-, CLF, BRF, BRCl, ICl. X-3, CLF3, BRF3, IF3, ICl3. XX-5, CLF5, BRF5, IF5. XX-7, IF7. These compounds can be prepared by the direct combination or by action of halogen on lower interhalogen compounds. Interhalogen compounds are covalent, volatile, unstable and dimagnetic in nature. Group 18 elements, noble gases of p block elements. Group 18 elements includes helium, neon, argon, krypton, xenon and radon. These elements are also called as noble or inert gases. All the elements of group 18 exist in the form of gases in atmosphere. About 1% by volume of air is occupied by noble gases. They are chemically unreactive. Noble gases are very stable electronic configuration. The valence shell electronic configuration of these elements is NH2NP6. Element helium, symbol He, atomic number 2. Condensed electronic configuration 1s2. Then neon Ne, atomic number 10. Condensed electronic configuration is He 2s2 2p6. Argon Ar 18. Ne 3s2 3p6. Krypton 36. Ar 3d10 4s2 4p6. Xenon Xe 54. Kr 4d10 5s2 5p6. Radon Rn 86. Xe 4f14 5d10 6s2 6p6. Physical properties. All the elements are colorless, odorless and tasteless. All the elements are always occurs in free and the free state in nature in monoatomic form. Atomic radii and tendency to liquefy increases on moving down the group. They require a very large amount of energy to remove an electron because of their stable electronic configuration. Hence, value of ionization enthalpy is very high. Noble gases have low melting and boiling point. They are slightly soluble in water, chemically unreactive due to completely filled valence shells, high and positive value of electron gain enthalpy and high ionization enthalpy. Noble gases do not take part in chemical reactions, that is, they are chemically unreactive elements. There are so many uses of noble gases in our daily life. You just finished your learning on p block elements with chemistry notes info podcast. Dear students, you can subscribe us, follow us to learn more and to learn chemistry, you can join us on Facebook, Instagram, YouTube, and you also subscribe our podcast for learning chemistry. Thank you to listening this podcast. This podcast is brought to you by Chemistry Notes Info. You can visit our website www.chemistrynotesinfo.com. You can also join us our Telegram channel, that is @chemistry notes info. Thank you to listening this podcast.